Welcome back. And today we are going to talk about more model improvements. Like we've been saying, it's easy using TensorFlow and Keras libraries to build a neural network. What's really tricky is to build one that works well. These are ways of improving your model. You don't really need it to build a running model, as we've demonstrated earlier, but they're fantastic sources of performance improvement when you actually need something that works well. We're going to go over 5 of the most commonly used model improvements: regularization, dropout, weight initialization, batch normalization, and learning rate decay. Okay, so regularization. Recall the loss function where we have an L that consists of data loss and regularization loss. And recall that the data loss measures our unhappiness with the classification outcome, and we've just been using regularization to penalize overly exotic models. Now, how does that work? Let's start with the question of why full loss can't just be data loss. What is the point of regularization loss? Why does it help models become more generalizable? So if your full loss was just the data loss, you could find a W such that your data loss is very small. A small loss means the classifier probably works well, but there's no guarantee that W is unique. You may find, given some value L, you may find many sets of weights W such that L is equally small for all of them. So in that situation, which set of weights do you choose? The regularization term is commonly defined as the sum of W squared across all of its elements. And this helps ensure that W does not overfit the dataset too much. Look at how this function works. Regularization penalizes weights with very large coefficients by squaring each weight coefficient. What this does is it penalizes models that rely too heavily on one weight or one neuron. So given some input X, let's use a more real example. Given input X and 2 vectors, or assume 2 matrices W1 here, and W1 which has values 1, 0, 0, 0, and W2 which has values 0.25, 0.25, 0.25, 0.25, which, all else being the same, which set of weights would be preferred? Put me on pause, think about it for a second. Using these values X and these values W, we calculate W1X, it has the score of 1. W2X has also a score of 1, so they're equally good. But regularization would tell us to prefer W2 over W1. Take a look at, run this calculation. The regularization score of W1 is 1 squared, 1. Regularization of W2 is 0.25 squared plus 0.25 squared, repeated, 0.25. And now remember, the smaller, this is a loss function, so the smaller this is, the better. So W2 is preferred. Why does that make sense? Well, think about it this way. With the first set of weights, the first feature has all influence over the output. The next 3 don't matter. With the second set of weights, all input features have some influence on the outcome. And that leads to a much more robust model, where the first model would be a bit more fragile, and the second model would be a bit more robust, meaning that if the data was wrongly encoded for this over here, you would be in serious trouble. Whereas here, even if the data was wrongly encoded, you would still have the other 3 features having some influence over the outcome. So in our example, we used something called L2 regularization, and that is because it's a default regularization method for a lot of machine learning libraries. There's also L1 regularization, which takes the absolute value of the values of W instead of the valued square. And there's also ElasticNet, another pretty common one you'll see. And if you take a look, it takes both L1 and L2 regularization into account, with some factor for determining the weightedness of the L2, the squared section. Kind of some interesting points of choice. For L2 regularization, it tends to produce non-sparse outputs. L1 regularization tends to produce more sparse outputs, and ElasticNet is a balance of both of these. All right, now let's talk about dropout. So dropout is really strange and really interesting. So the core concept behind dropout is if you randomly drop out neurons, your model performance improves. It really does. So think about why this might be true. First of all, deep learning models tend to overfit on patterns in the training data that may not exist in real data. And theoretically, the best way to fully regularize a model is to average the predictions of all possible settings of the parameters, weighing the setting by odds that it appears in the training data. If you had unlimited compute, that would totally work. You should read the original, this very classic paper on Dropout by Hinton and Shrivastava et al. Here's how Dropout works. So you take your standard neural network with, so this would be a input layer, 1 layer, 2 layers output, and you just suddenly start dropping neurons from the hidden layers and the input layer, where P is the probability of the retention of an individual neuron. Decent default p-value is 0.5 for the hidden layers, but you really want to keep almost all of the neurons in the input layer. So you might want to have a dropout of like a p of 0.9 or 0.95 here and 0.5 for the rest of everything. So this really oddly significantly improves the model's generalizability. And it's considered a subtype of regularization because it's kind of a ensemble, if you can think about it as a sort of ensemble method. So if you create many thin networks out of a single neural network, where if you use a p-value of 0.5, you can have 2 to the n powered thin networks out of a single neural network, the thin layers have very similar weights. And those layers with shared weights can be aggregated back into a single ensemble neural network at test time. This performs really well in image classification. So this we're pulling from this article here, this publication here. Without dropout, here is the classification error rate. With dropout, you get like almost maybe 0.75% improvement. And that's like really significant at this level. Why would this really help? So think about it intuitively. If you train many different neural networks and drop out every other neuron, you're forcing the model to build in redundant ways to encode the same data. You're making it less fragile. You're kind of spreading the prediction-ness across the entire network. You also want to break overly fragile associations in the neural network. So think about a situation where you were walking out in the street, you were holding vanilla ice cream, and suddenly out of nowhere, a dog like jumps up and like scares you. If you could never forget anything, you would always associate having ice cream and walking around with dogs attacking you. But that's probably only like a one-time situation. You've only been accosted by a dog while holding ice cream once in your life. If it happens over and over again in your life, it is maybe something you should take into account. But if it only happens once and our neural network like erases that memory that doesn't actually add any predictive power to your life, and it's very fragile association. So similarly, anything that's like overfitting, too niche, doing dropout will more or less like break all those too fragile associations. So this method of dropout is easier to explain, but there's another method called the inverted dropout method that is strictly preferred to dropout method as it improves test time performance. Think about what it takes to train 2 to the n sub-neural networks from a neural network. That performance is expensive. So it's kind of linked here how to implement inverted dropout, but the basic intuition is the same. Okay, next let's talk about weight initialization. We've been talking about this topic in a number of different ways. Recall that the weights initialization has a huge bearing of where you end up in convergence. Depending on where your weights initialize, your optimization function could start here, 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 here. And where it starts has a huge influence on like how long it takes until it reaches convergence, or whether it'll reach convergence at all. In all of our models so far, we've initialized small weights chosen from a Gaussian distribution, zero mean, unit variance. And that's like a not bad choice, but it's not really a great optimal choice. Choosing a good initialization W is still an active area of research. So far, it seems to be that a good W varies depending on which activation function you use. And this is important because if you think about parameter update functions, it is a function of the current weights, the activation function, and the learning rate you choose. So here is a good default that's not the Gaussian choice that you can use. The Xavier initialization is strictly preferred to the Gaussian distribution for sigmoid and tanh methods. Here is the paper linked again in the write-up so that you can better understand it. We're not really going to go deeply into how the Xavier initialization works, only that it is an improvement over the Gaussian and doesn't quite work on ReLUs, because if you recall, ReLUs, sigmoid and tanh are continuous functions, but ReLUs are 0 or x. So that's the one downside of this. If you use Keras, you can just use one of the built-in initializers, of which this is an option.
Okay, so now we've gone over dropout and regularization. How do we implement this in TF's DNN classifier? Super easy. These are both parameters. Read the documentation. Things are changing all the time with TF. But right now, learning rate and regularization depend on the optimizer you choose, which makes sense because that's where you build in the learning rate. And dropout is implemented at the estimator level, which also makes sense. So let's look at our spiral complex classifier. The way to add dropout, pretty straightforward. You just add the parameter call dropout equals whatever parameter 0.5 you choose. And you will have to, instead of just using default optimizer, you have to specify which optimizer you're using. So we're picking AndaGrab optimizer from the TF train library, setting a learning rate. This can also take the tensor as a value, which we're going to talk a bit about why you might want a learning rate value that changes over time when we talk about learning rate decay. And you can choose your regularization type. Here I've chosen L2 regularization strength at 0.001. That tends to be a pretty decent starting point for regularization. Now let's talk about batch normalization. Earlier, we talked about weight initialization, about how one way to do it is to just randomly choose from a Gaussian. Another way to do it is to choose a Xavier implementation. What if we could build a model that is less sensitive to this mumbo-jumbo juju of weight initialization, that's more robust to your choices of weight initialization? Batch normalization then comes in because it forces a nice distribution of activations at every layer of the deep learning network. This paper by these people whose names I can't pronounce is really fantastic, linked in the further documentation, walks you through the math of batch normalization. Theoretically, what is happening is when you choose your batch SGDs randomly, your inputs vary, and the difference cascades through the many layers of your network. The change in the distribution of network activations due to the change in network parameters during training is called internal covariate shift. What batch normalization does is it decreases internal covariate shift. So in more normal English, this crazy term, what is happening is at every layer, you are treating the activations and initializations of the next layer as a new neural network. And you are normalizing the inputs as they flow from one layer to another. So those inputs are also called activations, which is why that terminology gets thrown around a lot. Think back to when we first started talking about optimizing your learning process. We spoke about normalizing your input data in order to achieve a better training outcome. What batch normalization does is for each layer, it normalizes the inputs to the next layer. And intuitively, that leads to a more stable outcome. But yeah, this math is a little bit hairy. I won't blame you if you don't look over it too deeply. But if you do want to look at it more deeply, the paper's right here. So the other really neat thing about batch normalization is that it's a differentiable function, which means you can treat it as a layer in your deep learning model. So here, this little diagram here describes a model where we take some input, run it through a convolution layer, run it through the batch normalization layer, run it past a ReLU activation function and through a fully connected network to your output. This can be 4 layers, it can actually be more like 2 layers, but we can take this FC and we can layer one more con, we can layer one more batch norm, we can layer one more FC after it, and so on. It really makes the model, the impact of this is that the model becomes more robust to bad initialization choices. And sometimes, you're just randomly selecting your initializations. Even if you choose a Xavier initialization, you have no guarantee that the model will initialize your weights at a nice point in your loss landscape. Okay, now let's talk about learning rate decay. So earlier, a few slides ago, I told you something interesting, which is that you can define learning rate not as a fixed number, but as a tensor. And this is why you may want to implement learning rate decay. Think about all this pain in choosing a learning rate hyperparameter, all this guesswork involved. What if you could actually change the learning rate number as training goes on, and you can leap from this curve to this curve and more curves as things optimize. So instead of a loss function that follows a steady curve, what you would see is a loss function that might be approaching convergence, a change in your learning rate, might be approaching convergence, a change in your learning rate, and this is a final convergence. So I want you to take a second to think about why you would decay your learning rate and why you would never increase your learning rate over the epochs. Put me on pause, take a second. Alright, so you wouldn't increase your learning rate for the same reason that a golfer, once they hit the green, wouldn't switch back to the big woods golf clubs. When you're getting pretty close to your goal, you want to take smaller and smaller steps towards it. Much like you take a giant swing with your golf club when the target is 500 meters away, when you're 50 meters away, you don't want to take a gigantic golf club swing again. You actually want to start putting and taking it 10 meters, 5 meters, 2 meters at a time. And that is why exponential decay or 1/t decay works nicely for learning. Unfortunately, right now there is no very nice way to do it in our high-level estimator API in TensorFlow. You'll have to define learning rate decay as a layer in the TF layers API. That might have, just check the documentation again, by the time you're watching this video, someone very nice might have implemented it for you at the estimator level. We'll be spending a lot of time in the layers API when we go into convolutional neural networks because those can only be built at the layer level, not you can't just deploy them at the estimator level. Alright, it's time to get back to coding. So do these exercises to make sure you really understand how to improve your model. Create a new core data set, split your data into training, validation, and test data sets. Load it up on TensorBoard with monitoring set up so you can see performance per epoch. Implement dropout and regularization, see how that changes your model's training accuracy over time and your model's loss over time. And just like watch the model, tweak it, get back to it, develop some practice and some intuition around how to build and monitor and optimize these things. Alright, go!